something has changed 124 light-years away from Earth. The James Webb Telescope pointed its mirrors at the planet K2-18b, orbiting a red dwarf in the constellation Leo, and discovered a molecule that on our planet is produced exclusively by living organisms. Dimethyl Sulfide, a gas with a characteristic odor that is produced on Earth by seaweed and bacteria, a gas for which scientists know of no abiotic process of formation in the atmosphere of an Earth-like planet. And there it is, in the spectrum of a distant super-Earth, like a signature under the message we have been searching for so long. The data has been received. The analysis is complete, but there has been no official announcement for 3 months. NASA is silent. The European Space Agency is silent. And in the closed channels of the astronomical community, rumors are circulating about additional observations, the results of which are still being kept under wraps for reasons of strict scientific caution. What did James Webb see on K2-18b that made the greatest minds of our time pause before announcing what could be the discovery of the millennium? Stay tuned until the end, because you will find out what data caused the scientific community to hold its breath, why this discovery could rewrite our understanding of life in the universe, and what is behind NASA's silence over the past 3 months. And if this mystery has you as hooked as it has me, be sure to like and subscribe so you don't miss a single update as events unfold. Write in the comments where you are watching from, what time it is there, and what you think about this new discovery. And if you want to help the community grow, share this video on X, Facebook, Reddit, or just in your group chats. You are the reason we can continue to seek out stories like this. So thank you for your support. Let's start with what this planet, which has become the center of attention of the entire astronomical world, is all about. K2-18b was discovered in 2015 by the Kepler Space Telescope during its extended K2 mission. It is a super-Earth, a planet with a mass approximately 8.63 times that of Earth and a radius 2.6 times that of Earth. It orbits the red dwarf K2-18, a spectral class M star that is significantly cooler and dimmer than our Sun. The planet completes a full revolution around its star in 33 Earth days. And here's what's critically important. K2-18b's orbit is located right in the habitable zone of its star. This means that the temperature on the planet's surface theoretically allows liquid water to exist. It's not too hot for water to evaporate, not too cold for it to freeze forever. It is in this narrow range of distances from the star where conditions are suitable for life as we know it. But K2-18b is not alone in its system. It has a neighboring planet, K2-18c, which orbits closer to the star and is definitely too hot for life. Both planets revolve around their red dwarf at a distance of only 124 light-years from us. By cosmic standards, this is the neighborhood. Close enough that our most powerful telescopes can study the planet's atmosphere in detail that was unthinkable just 10 years ago. And it is this proximity, this accessibility for observation, that has made K2-18b one of the priority targets for the James Webb Telescope since it began its scientific work. The first hints of something unusual appeared back in 2019, when data from the Hubble telescope showed signs of water vapor in the atmosphere of K2-18b. This was a significant discovery in itself. Water vapor in the atmosphere of a planet in the habitable zone. One of the key ingredients for life, found where it can exist in liquid form on the surface. The scientific community responded with cautious optimism. Water vapor is important, but not enough. More data is needed. A more detailed analysis of the atmospheric composition is needed. And that's where James Webb, the most powerful space telescope ever launched by humankind, comes in. James Webb began its observations of K2-18b in 2023. Its infrared instruments, operating at wavelengths inaccessible to Hubble, have provided spectra of the planet's atmosphere with unprecedented detail. Every time the planet passes in front of its star, a small portion of the starlight passes through the planet's atmosphere. Gas molecules in the atmosphere absorb light at specific wavelengths, leaving characteristic fingerprints in the spectrum. It's like a chemical signature. Each molecule absorbs light in its own way, creating a unique pattern. By analyzing these patterns, we can determine what the atmosphere of a distant planet is made of without sending a single probe there. The results of James Webb's first observations were published and confirmed the presence of water vapor. But there was something else in the data: signs of methane. carbon dioxide. The atmosphere of K2-18b turned out to be rich in carbon and hydrogen. And here's where it gets interesting. Models showed that this planet could be a so-called Hycean world. Imagine a planet covered by a global ocean hundreds of kilometers deep. Beneath this ocean, under unimaginable water pressure, lies a mantle of exotic forms of ice that exist only under extreme conditions. And above the ocean is a dense hydrogen atmosphere, a world of water under a dome of hydrogen, a world where the boundary between the ocean and the atmosphere is blurred, where there is no solid surface in the sense we are familiar with. This discovery was exciting in itself. Hycean worlds are a theoretical class of planets whose existence had been predicted but never confirmed by observation. And now, K2-18b could become the first real example of such a world, an ocean planet under a hydrogen sky, a place radically different from Earth but potentially habitable, because where there is water, there can be life. At least, that is our working hypothesis, based on the only example we know of, our own planet. But the scientific community was slow to jump to conclusions. The interpretation of James Webb's data sparked debate. Some researchers pointed to alternative explanations for the observed spectral features. Perhaps this is not a Hycean world, but a mini Neptune with a dense atmosphere hiding a gas shell with no solid or liquid surface at all. Perhaps the hydrogen atmosphere is so dense and hot under pressure that no life can exist there. The debate continued. Additional observations were needed, and James Webb continued to watch. In the summer of 2024, the telescope conducted a series of additional observations of K2-18b. This time, different instruments and different spectroscopy modes were used to obtain the most complete picture of the atmospheric composition. Data was collected for months. Each transit of the planet in front of the star added new details to the spectrum. Astronomers were looking for confirmation of the presence of methane. They tried to determine the amount of water vapor. They checked for the presence of other molecules that could reveal chemical processes in the atmosphere. And in this data, in these carefully collected spectral lines, an anomaly appeared. A weak signal, barely discernible against the background noise, but statistically significant. A spectral line at a wavelength corresponding to the absorption of light by the dimethyl sulfide molecule. The formula of this molecule is 2 carbon atoms, 6 hydrogen atoms, and 1 sulfur atom. On Earth, dimethyl sulfide is produced by phytoplankton, microscopic marine algae that live in the upper layers of the ocean. It is a byproduct of their metabolism. It is a gas with a characteristic odor that we associate with the sea. And this gas, this biomarker, appeared in the spectrum of a planet 124 light-years away from us. The team analyzing the data checked the calculations many times. The spectral line was there, weak but stable. It was present in several independent observations. It was not an artifact or a data processing error. Dimethyl sulfide was indeed present in the atmosphere of K2-18b. And that's where the problem begins. Because for dimethyl sulfide, we don't know of a single natural abiotic process that could produce it in significant quantities in the atmosphere of a planet of this type. On Earth, this gas is produced by life, only by life. Volcanic activity does not produce it. Chemical reactions in the atmosphere do not create it. It appears where there is biological activity. And now it has been detected on a planet in the habitable zone of another star. Imagine the moment when the researcher first saw this spectral line on his screen. The first reaction was disbelief. Checking the data, recalibrating the instruments, searching for possible sources of contamination or systematic errors. But the line remained. Then came the realization of the magnitude of what this could mean. If it really is dimethyl sulfide, if the interpretation is correct, then this is potentially the first detection of a biosignature on an exoplanet. The first evidence that life exists beyond Earth. Not in our solar system, where we are looking for microbes under the ice of Enceladus or in the ancient lakes of Mars, but on a planet orbiting another star. Life in another planetary system. Life that arose independently of Earth. If confirmed, it would change everything. But science does not work on the basis of isolated discoveries and emotional reactions. Science requires reproducibility. It requires the exclusion of alternative explanations. It requires consensus in the scientific community before making an extraordinary claim. And the claim that we have discovered life on another planet is the most extraordinary claim imaginable. And so the team working with James Webb's data did not rush to the press with sensational headlines. They did what real scientists do. They began to methodically check every possibility, every alternative explanation before making any public statements. The first question that needed to be answered was, is this really dimethyl sulfide, or could the spectral line be caused by something else? Different types of molecules sometimes have spectral features at similar wavelengths. Could it be another molecule that we mistakenly took for dimethyl sulfide? The team conducted detailed modeling. They checked the spectra of all known molecules that could theoretically be present in the atmosphere of K2-18b. They looked for matches. The results showed that the most likely explanation for the observed spectral line was indeed dimethyl sulfide. Other molecules either did not match exactly or required conditions that contradicted other observations of the planet's atmosphere. The second question is, can dimethyl sulfide be formed in the atmosphere of K2-18b by abiotic means, by some process that we have not yet considered? This is a more complex question. The chemistry of exoplanetary atmospheres is an area where much remains unknown. We are only beginning to understand what reactions are possible in conditions that are radically different from those on Earth. A dense hydrogen atmosphere, high pressure, ultraviolet radiation from a red dwarf. Is it possible that in such conditions there is some exotic chemical pathway to the formation of dimethyl sulfide without the involvement of biology? The team brought in atmospheric chemistry experts. They ran computer models simulating chemical reactions under various conditions. And the result was discouraging. They could not find a single plausible abiotic mechanism that would produce dimethyl sulfide in the observed concentrations. This does not mean that such a mechanism does not exist. It only means that if it does exist, it is beyond our current knowledge and models. And this is where the dilemma arises. On the one hand, we have discovered a molecule that is a biomarker on Earth. On the other hand, we cannot completely rule out the possibility of an abiotic process unknown to us. What should we do in such a situation? Announce the discovery of a potential biosignature and risk being wrong? Or remain silent until we have additional, absolutely irrefutable evidence? The history of science is full of examples of hasty statements that later turned out to be wrong. Remember the situation with phosphine on Venus. In 2020, a group of researchers announced the discovery of phosphine in the atmosphere of Venus. Phosphine is another molecule that on Earth is produced mainly by biological processes. The discovery was presented as possible evidence of life in the clouds of Venus. The scientific community and the press reacted with great interest, but subsequent analyses revealed problems with the interpretation of the data. Other teams were unable to confirm the presence of phosphine. Doubts arose about the methods used to process the spectra. Gradually, the consensus shifted. It was most likely that the initial discovery was an artifact or the result of misinterpretation. Life on Venus once again became a purely speculative idea, and the researchers' reputation suffered. The team working with the K2-18b data remembers the phosphine story well. They understand that the price of error is enormous. To announce a biosignature and be wrong is not just a scientific embarrassment, it is a blow to public trust in science. It fuels skeptics and conspiracy theorists. It risks discrediting the entire field of extraterrestrial life search, and that is why they are acting with the utmost caution. They are conducting additional checks. They are looking for independent confirmation. They consult with colleagues. And until all these checks are complete, they do not make public statements. Hence the silence. Hence 3 months without official news, despite the fact that rumors have already leaked into the scientific community. But let's assume for a moment that the interpretation is correct. Let's entertain the idea that dimethyl sulfide on K2-18b really does have a biological origin. What does that mean? What picture of the world does that paint? Imagine a planet covered by a global ocean. There is hundreds of times more water there than on Earth. The ocean is so deep that at the bottom, under tremendous pressure, the water turns into exotic forms of ice, denser than liquid water. Above the ocean is a dense atmosphere consisting mainly of hydrogen mixed with water vapor, methane, and carbon dioxide. The star, a red dwarf, shines dimly but steadily. the planet receives about as much energy from its star as Earth receives from the Sun, despite its closer orbit, because the star is cooler. Microorganisms could exist in the upper layers of this ocean, where starlight can still penetrate the hydrogen atmosphere. Something similar to Earth's phytoplankton, organisms that use light energy for photosynthesis, producing organic molecules from carbon dioxide and water, and in the process of their metabolism, they release dimethyl sulfide as a byproduct, just as Earth's algae do. These organisms would not be similar to those on Earth. They evolved in radically different conditions. Under a hydrogen sky, in water saturated with methane, at a lower temperature and with a different light spectrum from a red dwarf. But the basic principles could be the same, using light energy to synthesize organic matter, releasing gaseous metabolic waste. If life exists on K2-18b, it is life that arose independently of Earth. The planet is 124 light-years away. No exchange of material between our worlds is possible. This would mean that life arose twice, at least twice, in our solar system and there, around the red dwarf K2-18. And if life arose twice within the reach of our telescopes, the statistical implications are staggering. How many more habitable worlds exist in the galaxy? How many planets where evolution has taken its course, creating life forms we cannot even imagine? But let's return to the reality of the observations and not get too far ahead of ourselves. Dimethyl sulfide has been detected. That is a fact, recorded in the data. The interpretation of this discovery is where the uncertainty begins, and the scientific community is divided. There are those who believe the data is compelling enough to seriously consider the biological hypothesis. There are those who insist on greater caution, pointing to gaps in our understanding of atmospheric chemistry. There are skeptics who believe that we still know too little about exoplanets to draw any conclusions about biomarkers. And there are optimists who see this as the beginning of a new era, an era when we will finally answer the question of whether we are alone in the universe. The key point is this: even if dimethyl sulfide on K2-18b is of biological origin, it does not mean that intelligent life or civilization exists there. We are talking about potential microorganisms, something perhaps no more complex than bacteria or single-celled algae. But even that would be a discovery of colossal proportions, because the discovery of even the simplest forms of life on another planet would answer one of the most fundamental questions ever asked by humankind. Is life unique to Earth, or is it common throughout the universe? Now let's dive into what's happening behind the scenes of the scientific process right now, as you listen to this video. James Webb's data is in the hands of several independent research teams. Each team is conducting its own analysis using its own processing and modeling methods. This is standard procedure in astronomy, especially when it comes to potentially revolutionary discoveries. The goal is to reach a consensus. If several independent teams, using different approaches, come to the same conclusion, it significantly increases confidence in the result. Conversely, if interpretations differ, it is a signal that additional data or a deeper understanding of the problem is needed. According to unofficial information circulating in astronomical circles, at least 2 independent groups have confirmed the presence of dimethyl sulfide in their data analyses. The spectral line is stable. It does not disappear when different processing methods are used. This is a good sign. But confirming the presence of the molecule is only the first step. The next step is to understand its origin, and this is where the differences begin. Some researchers believe that the biological hypothesis is the most plausible based on the available data. Others insist that we must consider all possible abiotic explanations, however unlikely they may seem, before resorting to biology. There is another factor complicating the situation: data quality. The spectral line of dimethyl sulfide is weak. It is at the limit of sensitivity of James Webb's instruments. To increase confidence, additional observations are needed. More transits of the planet in front of the star, more hours of observation to accumulate the signal and reduce noise. And such observations are planned. James Webb will return to K2-18b in the coming months to collect more data. Each new observation will either strengthen the case for dimethyl sulfide or cast doubt on it. And only after accumulating a sufficient amount of data will the scientific community be able to make a final conclusion. What if it really is life? What if, in a few months or a year, NASA and its partners announced that dimethyl sulfide on K2-18b has been confirmed, and the most likely explanation is biological. How will the world change after such an announcement? It will be a moment that will go down in history books. The moment when humanity learned that it is not alone in the cosmos, not in the sense of meeting humanoid aliens, but in the sense of realizing that life is not an accident, not a unique oddity that happened once on one planet, but a universal phenomenon that occurs wherever the conditions are right. The religious, philosophical, and cultural implications of such a discovery are difficult to overestimate. For some, it will confirm long-held beliefs that the universe is full of life, that we are just one thread in a vast cosmic tapestry of biology. For others, it will raise existential questions about humanity's place in the cosmos, about the meaning and purpose of our existence. For science, it will open up a whole new field of research: xenobiology, the study of life that arose independently of Earth. What will its biochemistry be like? Does it use DNA or some other mechanism for storing genetic information? How did it evolve in conditions so different from those on Earth? More importantly, this discovery will set the direction for future searches. If life is found on K2-18b, the logical next step is to look for it on other exoplanets in habitable zones. Next-generation telescopes, such as NASA's planned Habitable Worlds Telescope, will be specifically designed to detect biosignatures. We will begin to catalog living worlds, and who knows, maybe among them will be planets with more complex life forms. Maybe someday we will discover not just microbes, but something more. But those are dreams for the distant future. Right now, we are on the threshold, waiting for confirmation or refutation, waiting for science to do its job. It is important to understand that the scientific process is slow by nature, especially when the stakes are so high. Researchers cannot afford to rush. Every claim must be backed up by data. Every interpretation must be checked and double-checked. And that's right. Because a mistake here is not just a scientific anomaly, it is a blow to society's trust in the scientific method. And so we wait. We wait for additional observations. We wait for independent confirmation. We wait for the moment when the scientific community is ready to say with a high degree of certainty, yes, this is a biosignature, or no, it's something else. While we wait, speculation continues. Discussions are raging on scientific blogs, at conferences, and in closed email lists of astronomers. Each new analysis of the data brings new details. Each atmospheric model adds nuances to our understanding. And gradually, slowly, the picture becomes clearer. Not as quickly as enthusiasts and journalists hungry for sensational news would like, but with the cautious methodicalness that characterizes real science at the forefront of discovery. And here's what makes this situation particularly exciting. We are living in this moment in history. We are watching events unfold in real time. Perhaps in a few months, we will look back on this period as the moment when everything changed. Or perhaps we will remember it as yet another case of hope colliding with the harsh reality of data uncertainty. But regardless of the outcome, the very fact that we can discuss a potential biosignature on a planet 124 light-years away speaks to how far science has come. 20 years ago, we didn't even know exoplanets existed. Now we are studying their atmospheres and looking for signs of life. Now let's dive into the details of what dimethyl sulfide is and why its detection is so important for understanding potential life on K2-18b. The dimethyl sulfide molecule has a relatively simple structure. 2 carbon atoms are bonded to a sulfur atom, and each carbon atom carries 3 hydrogen atoms. This configuration creates a volatile compound with a low boiling point, which means that under Earth-like conditions, dimethyl sulfide easily transitions into a gaseous state and enters the atmosphere. On our planet, marine ecosystems are the main source of this gas. Phytoplankton, microscopic algae drifting in the upper layers of the ocean, produce dimethyl sulfide by breaking down another sulfur-containing compound called dimethyl sulfonio-propionate. This substance serves as an osmolyte for plankton, helping to regulate osmotic pressure in cells. When algae cells break down or metabolize this compound, dimethyl sulfide is formed. This process is not accidental and has ecological significance. Dimethyl sulfide, entering the atmosphere, serves as a source of sulfur for the formation of cloud condensation nuclei. Tiny sulfate particles formed from dimethyl sulfide in the atmosphere become centers around which water vapor condenses, forming cloud droplets. Thus, biological activity in the ocean affects the planet's cloud cover, which in turn affects the climate by changing the reflectivity of the atmosphere. This is an example of how life can change the planetary environment, creating feedback loops between the biosphere and the atmosphere. And here's what's critically important. We don't know of any abiotic process on Earth that produces dimethyl sulfide in significant quantities. Volcanoes emit sulfur-containing gases, but these are mainly hydrogen sulfide and sulfur dioxide, not dimethyl sulfide. Geothermal sources and hydrothermal systems also do not produce this gas. When we look at K2-18b and see dimethyl sulfide in its atmosphere, we are faced with the question, could a similar biological process exist there? The planet is radically different from Earth. It does not have a solid surface in the usual sense. It is a Hycean world, where the ocean transitions into a hydrogen atmosphere without a clear boundary. The pressure at different depths in the ocean varies from relatively low near the surface to monstrously high at depths of hundreds of kilometers, where the pressurized water turns into exotic forms of ice. The temperature profile is also different. The red dwarf emits mainly in the infrared range rather than in visible light like our sun. This means that any photosynthetic organism on K2-18b would have to adapt to using infrared light for energy. But despite all these differences, the basic chemical ingredients for life are present there. Water is abundant. Carbon is present in the form of methane and carbon dioxide. Hydrogen is abundant in the atmosphere. Energy comes from the star, albeit in a different spectral range. And if life exists on K2-18b, it could occupy a niche similar to that of Earth's phytoplankton, organisms drifting in the upper layers of the ocean, where the star's light is still strong enough for photosynthesis, using the available chemical elements to build their cells and metabolize. And just as Earth's phytoplankton releases dimethyl sulfide, hypothetical life on K2-18b could produce the same gas as a byproduct of its metabolic processes. This does not mean that this life would be identical to Earth's. On the contrary, it almost certainly evolved along a completely different evolutionary path. But convergent evolution could have led to similar chemical solutions to similar environmental problems. However, before we get too carried away with the biological hypothesis, we need to seriously consider alternative explanations. The science of exoplanets is still young, and our understanding of chemical processes in exotic atmospheres is far from complete. Perhaps there is some abiotic pathway to dimethyl sulfide formation that we simply haven't discovered yet. Let's explore that possibility. One proposed mechanism involves photochemical reactions in the upper atmosphere. Ultraviolet radiation from the star can break down methane and hydrogen sulfide molecules, creating highly reactive radicals. These radicals can then recombine to form various organosulfur compounds, including, theoretically, dimethyl sulfide. But calculations reveal a problem. The efficiency of such photochemical pathways is extremely low under the conditions we observe on K2-18b. The concentration of dimethyl sulfide detected in the data significantly exceeds what would be expected from purely photochemical processes. Another proposed explanation is related to volcanic or geothermal activity. On Earth, volcanoes emit a wide range of gases, and although dimethyl sulfide is not a major component of volcanic emissions, it could theoretically be formed under certain conditions. But K2-18b is not an Earth-like planet with a solid crust and volcanoes. It is an ocean world with a mantle of high-density ice. Geological activity there, if it exists at all, would be radically different from that on Earth. And even if we assume the existence of some form of hydrothermal activity at the boundary between the liquid ocean and the icy mantle, the question remains: could such activity produce dimethyl sulfide in the quantities observed? Modeling has not yet provided a convincing answer. The third possibility that researchers are considering is related to impact processes. Asteroids and comets falling on the planet could bring organic molecules, including sulfur-containing compounds. Upon impact, these molecules could be released into the atmosphere. But there are problems here as well. First, the frequency of impacts on K2-18b is unknown. Second, even if impacts do occur, dimethyl sulfide is not a common component of comets and asteroids. It is unstable, and decomposes rapidly under the influence of cosmic radiation. And third, if dimethyl sulfide came from external sources, we would expect to see other organic molecules brought in by the same impactors. But the spectra show dimethyl sulfide, not the whole set of organics we would expect from impacts. Thus, each alternative explanation faces difficulties. None of them can convincingly explain the observed concentration of dimethyl sulfide without resorting to additional, as yet unconfirmed assumptions. This is where a principle known as Occam's razor comes into play. All other things being equal, the simplest explanation, requiring the fewest additional assumptions, is most likely correct. On Earth, dimethyl sulfide is produced by life. We know that this works. We understand the mechanism. We observe it every day in our oceans. If conditions suitable for life exist on K2-18b and we detect a molecule there that is a biomarker on Earth, then the biological hypothesis becomes the most economical explanation. But science does not operate on the basis of simplicity. Science requires evidence, and so the debate continues. It is important to understand that the discovery of dimethyl sulfide is not the only intriguing feature of K2-18b's atmosphere. James Webb's spectra also showed the presence of methane in concentrations that are difficult to explain by purely abiotic processes. On Earth-like planets, methane is usually quickly oxidized in the atmosphere, turning into carbon dioxide and water. To maintain a significant concentration of methane, a constant source is needed to replenish losses from oxidation. On Earth, this source is largely biological activity. Methanogenic bacteria living in oxygen-free conditions produce enormous amounts of methane. Of course, methane can also be formed abiotically, for example, as a result of geological processes known as serpentinization. But the ratio of methane to other gases in the atmosphere of K2-18b raises questions. The combination of methane and dimethyl sulfide in the same atmosphere is particularly interesting. If both gases are of biological origin, this could indicate the presence of a complex ecosystem with different types of organisms, some producing methane, others producing sulfur-containing compounds. We see a similar picture on Earth. Methanogenic bacteria live in anaerobic conditions, such as swamps and marine sediments, while phytoplankton in aerobic conditions produce dimethyl sulfide. Could there be a similar division of ecological niches on K2-18b? Perhaps methane-producing organisms inhabit the depths of the ocean, where light does not penetrate and oxygen is absent. And in the upper layers, illuminated by the star, organisms that produce dimethyl sulfide live. This is pure speculation, of course, but it is speculation based on what we know about life on Earth and the chemistry of atmospheres. Let's now turn to the question of how habitable a planet like K2-18b is in principle. This is one of the most hotly debated questions in astrobiology right now. Traditionally, the search for life has focused on Earth-like planets, rocky worlds with solid surfaces, thin atmospheres, and oceans of liquid water. Earth is our only known example of a habitable planet, so it's natural that we look for worlds similar to our own. But K2-18b challenges this paradigm. It is not an Earth-like planet. It is something else. A world with a global ocean hundreds of kilometers deep and a dense hydrogen atmosphere. Could such a world be habitable? The answer is not obvious. On the one hand, K2-18b has the key ingredients for life. Liquid water is abundant. Carbon is present. Energy from the star is available. The planet is in the habitable zone, where temperatures allow water to exist in a liquid state. That's good news. But there are also problems. The dense hydrogen atmosphere creates a strong greenhouse effect. The temperature on the ocean's surface could be significantly higher than comfortable conditions for Earth-like life, possibly exceeding 100 degrees Celsius in some regions. The pressure at different depths in the ocean varies so much that the physical and chemical conditions change radically with depth. At great depths, the pressure is so high that water transforms into exotic forms of ice that are denser than liquid. This creates stratification, layers of water with different properties that do not mix easily. Another potential problem is related to radiation from the red dwarf. Stars like red dwarfs are known for their flare activity. They can emit powerful bursts of X-ray and ultraviolet radiation that bombard planets in close orbits. Such radiation can destroy complex organic molecules and create a hostile environment for life on the surface. However, The dense hydrogen atmosphere of K2-18b could serve as a protective shield, absorbing much of the harmful radiation before it reaches the ocean. In addition, if life exists in the ocean, even a shallow depth of water provides effective protection from radiation. Water is an excellent shield against radiation. At a depth of just a few meters, the radiation dose drops to safe levels. There is also the question of nutrient circulation. On Earth, life in the ocean depends on water circulation, which brings nutrients from the depths to the surface, where photosynthesis occurs. This is achieved through processes known as upwelling, when deep waters rise to the surface, enriching the upper layers with minerals and nutrients. On K2-18b, ocean circulation may be completely different due to extreme depth and high pressure. Water stratification could prevent mixing between the deep and surface layers. This would pose a problem for hypothetical life. Where would nutrients come from if they are locked away in the depths and do not rise to the lighted surface? One possible solution is hydrothermal activity. If hydrothermal systems exist at the boundary between the liquid ocean and the icy mantle, they could serve as a source of minerals and energy, creating local ecosystems independent of starlight. But even if conditions on K2-18b are far from ideal by Earth standards, that doesn't mean life is impossible there. Life on Earth demonstrates an amazing ability to adapt to extreme conditions. We find microorganisms in boiling geysers, in icy polar lakes, in the depths of the ocean under pressures of hundreds of atmospheres, in highly radioactive environments, and in acidic and alkaline waters. Extremophiles, as we call them, show that life can thrive in conditions that would seem completely unsuitable. And if life on Earth, which evolved for moderate conditions, can adapt to such extremes, then why couldn't life that originated on a planet with initially extreme conditions be adapted to them from the very beginning? Imagine an organism that evolved in the conditions of K2-18b. Its biochemistry would be optimized for high temperatures, high pressure, and infrared light. Its metabolism would use the available chemical resources: hydrogen, methane, carbon dioxide, and sulfur. Its structure would be resistant to radiation thanks to protective mechanisms developed through evolution. For such an organism, the conditions on K2-18b would not be extreme, but normal. Moreover, conditions on Earth would seem extreme and unsuitable for life. Too low pressure, too little hydrogen in the atmosphere, too much oxygen, which could be toxic to it. This reminds us that our idea of habitability is deeply anthropocentric. We define habitability based on what is suitable for life on Earth. But the universe may be full of life forms adapted to conditions that we consider impossible. This is where the story takes an even more intriguing turn. Even if dimethyl sulfide on K2-18b is of biological origin, even if life exists there, we face a fundamental problem. How can we confirm this definitively? The discovery of a single biomarker, however convincing, is not irrefutable proof. Science requires multiple independent lines of evidence. What else could we look for in the atmosphere of K2-18b that would strengthen the case for biology? One approach is to look for other biomarkers. If phytoplankton produces dimethyl sulfide, it probably also produces oxygen through photosynthesis, as Earth's plants and algae do. Oxygen is an extremely reactive gas that is quickly consumed in chemical reactions. To maintain a significant concentration of oxygen in the atmosphere, a powerful biological source is needed to constantly replenish losses. The search for oxygen in the atmosphere of K2-18b is one of the priorities for future observations. However, there is a complication here. Oxygen can also be formed abiotically through the photodissociation of water. Ultraviolet radiation breaks down water molecules, releasing oxygen. This is a process that does not require life. To distinguish biogenic oxygen from abiotic oxygen, it is necessary to analyze isotope ratios and look for other gases that would react and disappear in the presence of oxygen. For example, methane and oxygen are chemically incompatible. They react with each other to form carbon dioxide and water. If we see both gases simultaneously in the atmosphere, methane and oxygen, this is a strong indicator that both are constantly being replenished by some active processes. On Earth, these processes are biological. Plants produce oxygen, and bacteria and other organisms produce methane. If future observations detect oxygen in the atmosphere of K2-18b, along with the methane and dimethyl sulfide already detected, this would make a very compelling case for biology. 3 different biomarkers, each of which is difficult to explain abiotically, especially in combination, would be powerful evidence. But even then, skeptics might demand even more evidence. Exotic abiotic mechanisms could be proposed. Doubts about the interpretation of the data could be raised. And that's okay. That's how science works. Extraordinary claims require extraordinary evidence, and the claim of finding life on another planet is the most extraordinary claim imaginable. Another approach to confirming life on K2-18b is to look for temporal variability in gas concentrations. If life exists, its metabolic activity may vary depending on conditions. For example, on Earth, the production of dimethyl sulfide by phytoplankton varies depending on the season, water temperature, and the availability of nutrients. If we observe K2-18b over a long period of time and see that the concentration of dimethyl sulfide fluctuates, this could indicate biological processes responding to changes in the environment. Of course, abiotic processes can also exhibit variability. For example, volcanic activity is not constant. But the pattern of variability, its correlation with other observable parameters, could provide clues about the nature of the processes. Another intriguing possibility is the search for spectral signatures of chlorophyll or its analogs. Chlorophyll is a pigment used by plants and algae on Earth for photosynthesis. It has a characteristic spectrum of light absorption and reflection. In particular, chlorophyll strongly absorbs blue and red light, but reflects green light, which gives plants their color. If photosynthetic organisms exist on K2-18b, they could use pigments adapted to the infrared light from the red dwarf. These pigments would have their own spectral characteristics. Detecting such features in the reflected light from the planet would be powerful evidence for biology. However, this is an extremely difficult task technically. The reflected light from an exoplanet is extremely faint compared to the light from the star, and isolating it requires next-generation instruments that are still under development. Wait until you hear what else they found in James Webb's data. In addition to dimethyl sulfide, methane, and water vapor, the spectra showed traces of ammonia. Ammonia is another molecule that can have both biological and abiotic origins. On Earth, some bacteria produce ammonia through nitrogen fixation, converting atmospheric nitrogen into a form that plants can use. Ammonia can also be produced by the decomposition of organic material, but ammonia is unstable in the presence of oxygen and oxidizes quickly. Its presence in the atmosphere of K2-18b, if confirmed by further observations, adds another layer of complexity to the interpretation of the planet's chemistry. Is ammonia a product of biological processes, or is it formed abiotically in the depths of the ocean and released into the atmosphere through some geological process? Once again, we are faced with uncertainty that requires more data to resolve. The atmospheric chemistry of exoplanets is proving to be an incredibly complex science. Every new molecule we discover raises new questions. Every spectral line requires interpretation, and there can often be more than one interpretation. It is not simply a question of measurement, is there a molecule or not? It is a question of understanding. Where did it come from? How does it interact with other components of the atmosphere? What does its presence tell us about the processes taking place on the planet? And for all this, we need not only observational data, but also theoretical models, laboratory experiments testing chemical reactions under extreme conditions, and computer simulations modeling atmospheric processes. It is interesting to note that K2-18b is not the only exoplanet where biosignatures are being sought. James Webb observes many other worlds in the habitable zones of their stars. Some of them are super-Earths, like K2-18b. Others are Earth-sized planets orbiting red dwarfs. Each of these planets has its own atmospheric chemistry and unique characteristics. With each new observation, we learn more about the diversity of planetary worlds in the galaxy. We are beginning to understand that planets are not simply divided into terrestrial and gas giants. There is a whole spectrum of intermediate types: mini-Neptunes with dense atmospheres, Gaian ocean worlds, lava planets with molten surfaces, planets with atmospheres composed of exotic gases not found in our solar system. And here's what's truly exciting. K2-18b may be just the first example of a whole class of habitable worlds that we are beginning to discover. If Gaian planets can support life, it radically expands the number of potentially habitable worlds in the galaxy. Until now, the search for life has focused on Earth-like planets, which are relatively rare. But if we add Gaian worlds to the list, the number of candidates increases by orders of magnitude. Mini-Neptunes and super-Earths with dense atmospheres and global oceans may be much more common than Earth-like planets. And if even a small fraction of them are habitable, the galaxy may be teeming with life in forms and places we have not even considered. Let's now turn to the question of what's next in the study of K2-18b. As I mentioned, James Webb has planned additional observations of this planet in the coming months. These observations will use different instruments and modes to obtain more detailed spectra in different wavelength ranges. The goal is to confirm the presence of dimethyl sulfide with higher statistical significance, search for other biomarkers such as oxygen, and obtain more accurate measurements of the concentrations of gases already detected. Each new observation will add hours of exposure time, accumulating signal and reducing noise. The more data we have, the more confident we can be in our conclusions. Parallel to the observations, theoretical work continues. Researchers are developing increasingly complex models of the atmosphere of K2-18b, including detailed chemistry, radiation transfer, and cloud processes. These models help predict what spectral features we should expect to see in different scenarios. For example, if there really is biology on the planet that produces dimethyl sulfide, the models can predict what other gases should be present and in what proportions. These predictions are then compared with actual observations. The correspondence between the model and the data strengthens the confidence in the interpretation. Discrepancies indicate that something is missing from the model or that the interpretation needs to be revised. Another aspect of the research is laboratory experiments. In laboratories on Earth, scientists recreate conditions similar to those on K2-18b and study what chemical reactions are possible. They place mixtures of gases, hydrogen, methane, ammonia, water vapor, in high-pressure chambers, irradiate them with ultraviolet light, heat or cool them, and see what molecules are formed. This provides empirical data on the possible abiotic pathways for the formation of various compounds. If laboratory experiments show that dimethyl sulfide is easily formed under K2-18b conditions without the involvement of biology, this will weaken the biological hypothesis. If, on the contrary, the experiments confirm that abiotic formation is extremely unlikely, this will strengthen the case for biology. Independent research groups around the world are working on analyzing the same data from James Webb. This is standard practice in astronomy. Data from large telescopes becomes publicly available after a period of exclusive access for the team that conducted the observations. After that, any researcher can download the data and conduct their own analysis. This is important for the scientific process. Different teams use different data processing methods, different models, and different approaches to interpretation. And if several independent teams come to the same conclusions, it significantly increases confidence in the result. In the case of K2-18b, we are awaiting publications from several groups that will confirm or refute the presence of dimethyl sulfide and give their interpretations. The scientific publication process also adds a layer of verification. When researchers are ready to present their results, they submit an article to a scientific journal. The article goes through a peer review process, where experts in the field critically evaluate the methods, data, analysis, and conclusions. Reviewers may request additional checks, further analysis, or clarification of interpretations. This process can take months. Only after an article has been peer-reviewed and accepted for publication are the results considered officially presented to the scientific community. That is why we have not yet seen an official announcement from NASA or James Webb's team about the discovery on K2-18b. The articles are still in the process of being prepared and reviewed. Until they are published, the teams are cautious in their public statements. However, rumors and preliminary discussions are leaking out. Researchers present preliminary results at scientific conferences. Unpublished data circulates in closed email lists. Journalists following the topic pick up hints and publish articles based on unofficial sources. This creates a situation where the scientific community knows more than has been officially announced, but cannot speak openly until the formal process is complete. This creates tension between the desire to share exciting discoveries and the need to adhere to scientific rigor and procedures. What will happen if we receive final confirmation in a few months? Imagine this moment: a NASA press conference broadcast around the world. The director of science missions takes the podium, followed by graphs of spectra, data tables, and artists' impressions of the distant planet appearing on the screen. And then the words that humanity has been waiting for millennia are spoken. We have found compelling evidence of biological activity on a planet outside our solar system. K2-18b, a super-Earth 124 light-years away in the constellation Leo, shows atmospheric biosignatures that are most plausibly explained by the presence of life. Dimethyl sulfide has been confirmed by multiple independent observations. Additional biomarkers have been detected. Alternative abiotic explanations have been carefully considered and found to be unlikely. The scientific consensus has been reached. We are not alone. How will the world react to such an announcement? It depends on many factors: how the information is presented, how convincing the evidence is, and how confident the scientific community is. If the statement is cautious, leaving room for doubt, the reaction may be muted. People will remember the story of phosphine on Venus and be skeptical. They will wait for additional confirmation before accepting a revolutionary idea. But if the statement is strong, if multiple independent lines of evidence converge on a single conclusion, if the world's leading experts express a high degree of confidence, then the reaction will be completely different. It will be the #1 news story in every media outlet on the planet. Social media will explode with discussion. Philosophers, theologians, scientists, and ordinary people will debate the implications of the discovery. For science, this will open a new era of research. Astrobiology, a field that has existed mainly at the theoretical level until now, will become a full-fledged empirical science with a real object of study. New questions will arise that demand answers. What is the nature of life on K2-18b? How complex is it? Does it use DNA or some other mechanism for storing genetic information? What is its biochemistry? How has it adapted to the conditions of the Gaian world? Does it have a cellular structure? Is there multicellular life there, or only single-celled organisms? And the most exciting question: could life on K2-18b have evolved into more complex forms? Are there analogs of animals, plants, and fungi there? Of course, it is impossible to answer most of these questions with telescopic observations alone. Spectroscopy of the atmosphere can tell us about its chemical composition, the presence of biomarkers, and possibly some aspects of the metabolism of organisms if they produce large enough quantities of gases. But the details of biology will remain a mystery until we can study this life directly. And this raises the question: is a mission to K2-18b possible? 124 light-years is a huge distance. Even if we could travel at the speed of light, which is physically impossible according to our current understanding, the journey would take 124 years. With the realistic technologies we can imagine in the foreseeable future, such a mission would take tens of thousands of years. But that doesn't mean we're helpless. Next-generation telescopes will have even greater capabilities. The Habitable Worlds Telescope, developed by NASA, is specifically designed to directly observe Earth-like exoplanets and analyze their atmospheres in great detail. It will be able to detect fainter spectral lines and distinguish finer details of atmospheric composition. The European Space Agency is planning the Plato mission, which will search for exoplanets and characterize their properties. Extremely large ground-based telescopes, such as the Extremely Large Telescope in Chile, with a mirror diameter of 39 meters, will be able to complement space observations. With each new generation of instruments, we will learn more and more details about K2-18b and other potentially habitable worlds. Moreover, the discovery of life on K2-18b will catalyze the development of new technologies. If we know that life exists there, it creates an incentive to develop ways to study it. Perhaps we will see the emergence of interstellar probes using revolutionary propulsion technologies, laser sails accelerated by powerful ground-based lasers to a significant fraction of the speed of light, or fusion engines using controlled nuclear fusion to achieve high speeds. The Breakthrough Starshot project is already considering the possibility of sending miniature probes to the nearest star system, Alpha Centauri, using laser sails. If the technology proves viable, it could be scaled up for more distant missions. Of course, even with such technologies, the journey to K2-18b would take decades, and we would only receive the results more than a century after launch. But for humanity, looking at the prospect of centuries, this may be an acceptable price to pay for the direct study of extraterrestrial life. Let's entertain an even more ambitious idea for a moment. What if K2-18b hosts not just microbial life, but something more complex? What if multicellular organisms have evolved there? On Earth, the journey from the first microbes to multicellular forms took billions of years. Single-celled life appeared about 3/8 of a billion years ago. Multicellular organisms arose much later, about 600 million years ago. It was a long journey that required many evolutionary innovations, the development of cell specialization, mechanisms of intercellular communication, and systems of coordination between cells. On K2-18b, evolution could have taken a completely different path. Conditions there are radically different from those on Earth, and this could have led to completely different evolutionary solutions. Imagine the ocean of K2-18b, illuminated by the dim red light of the star seeping through the dense hydrogen atmosphere. In the upper layers of this ocean, organisms drift, capturing infrared photons and converting their energy into the chemical bonds of organic molecules. These organisms could be similar to Earth's plankton, but adapted to completely different conditions. Their pigments would absorb infrared light instead of visible light. Their cell membranes would be resistant to high temperatures and pressures. Their metabolism would use hydrogen from the atmosphere as a reducing agent instead of the compounds traditional for Earth life. And perhaps, over time, some of these organisms would have joined together in colonies, developing primitive multicellularity. The colonies could have differentiated. Some cells would have specialized in photosynthesis, others in absorbing nutrients, and still others in reproduction. If evolution on K2-18b continued long enough, more complex forms could have appeared. Organisms with tissues and organs performing specialized functions. Perhaps something similar to animals. Heterotrophs, feeding on other organisms, floating in the water column in search of food. Their forms would be adapted to life in a dense hydrogen atmosphere and high-density water. Perhaps they would have developed sensory organs that perceive infrared radiation, chemical gradients, and vibrations in the water. Perhaps they would have developed ways to communicate and exchange signals with their fellow creatures. This is all pure speculation, of course. We have no idea whether anything more complex than simple microbes exists on K2-18b. But the very fact that we can seriously discuss such possibilities shows how far we have come in our understanding of exoplanets and the potential for life in the universe. It is also important to consider the timescale. The star K2-18 is a red dwarf, and such stars have extremely long lifespans. While our Sun will exist for about 10 billion years, red dwarfs can shine for trillions of years. This means that life on planets around red dwarfs has much more time to evolve. If life on K2-18b appeared early in the planet's history, it had billions of years to develop. Over such a period of time, evolution can produce an incredible variety of forms and adaptations. On Earth, over 3 8/10 of a billion years, evolution has progressed from the simplest bacteria to humans. Imagine what could happen over even more time on a planet with completely different conditions. On the other hand, evolution on K2-18b may have faced obstacles that did not exist on Earth. Flares from the red dwarf could periodically sterilize the upper layers of the ocean, killing all life and forcing life to start over each time. The lack of a solid surface could have limited evolutionary possibilities. On Earth, the emergence of life on land opened up completely new ecological niches and led to an explosive growth in diversity. On a planet without land, this stage would never have happened. Ocean stratification could have created isolated layers with different conditions, preventing the exchange of genetic material between populations and slowing down evolution. All of these factors could have influenced the trajectory of life, if it exists there. Now let's talk about the broader implications of the discovery of life on K2-18b for our understanding of the prevalence of life in the universe. If life is found on the second planet we have studied in detail for biosignatures, it radically changes the statistics. It would mean that life is not an incredible rarity, but rather a common occurrence wherever the right conditions exist. Astronomers use the Drake equation to estimate the number of intelligent civilizations in the galaxy. This equation includes several factors: the rate of star formation, the fraction of stars with planets, the number of planets in the habitable zone per star, the fraction of such planets where life arises, the fraction of planets with life where it evolves into intelligent forms, and so on. The most uncertain factor has always been the proportion of planets where life arises. Until now, we knew of only one example: Earth. This made it impossible to estimate the probability of life arising. Perhaps life arises on every planet with the right conditions, making it virtually inevitable, or perhaps the emergence of life is an incredibly unlikely event, requiring such a specific set of circumstances that it only happens once in billions of planets. The discovery of life on K2-18b would give us a second data point, and 2 data points are enough to draw a line. If life exists there and here, and both planets are inhabitable zones with liquid water, it suggests that life arises fairly easily when the right conditions are present. That would mean there could be millions, if not billions, of habitable worlds in our galaxy. Of course, the discovery of microbial life does not automatically imply the existence of intelligent civilizations. The path from microbes to intelligent beings can be extremely long and fraught with obstacles. On Earth, microbes existed alone for billions of years before multicellular forms appeared, and it took several 100 million years more for the first multicellular organisms to evolve into intelligent beings. Even then, intelligence arose in only one evolutionary line out of the millions of species that existed. This may mean that microbial life is common, but intelligent life is extremely rare. Or perhaps, given enough time and the right conditions, evolution inevitably leads to intelligence. We simply don't know. But every new discovery brings us closer to the answer. There is another aspect worth considering: the philosophical and existential implications of discovering extraterrestrial life. For millennia, humanity considered itself the center of creation, unique beings with a special place in the cosmos. The Copernican revolution showed that Earth is not the center of the universe. The discovery that we revolve around an ordinary star at the edge of an ordinary galaxy stripped us of our cosmological exclusivity. Evolutionary biology showed that humans are just one branch on the tree of life, linked by a common origin to all other organisms on Earth. This stripped us of our biological exclusivity. The discovery of life on another planet will be the next step in this process of deconstructing human exceptionalism. It will show that life is not a unique feature of Earth, that we are not the only living beings in the cosmos. For some, this will be a deeply unsettling realization. The idea that we are not unique, that our planet is not special, that somewhere out there are other forms of life evolving according to their own laws, can cause a feeling of insignificance, a loss of meaning. If life is common in the universe, what makes humanity special? What is the purpose of our existence in a cosmos full of other living worlds? These questions will be debated by philosophers, theologians, and psychologists. Religious traditions, many of which are built around the idea of a special relationship between God and humanity, will face the need to rethink their doctrines in light of the existence of extraterrestrial life. Some religions have already prepared a theological framework for such a possibility. Others will face a serious challenge, but for many others, the discovery of extraterrestrial life will be a source of inspiration and awe. The realization that the universe is full of life, that we are part of a much larger cosmic history of biology, can give new meaning to our existence. We are not alone. We are not an accident. Life is a fundamental feature of the universe, arising wherever the conditions are right. This is a majestic and beautiful idea. It expands our sense of connection to the cosmos. It makes the universe not cold and empty, but alive and full of potential. And it can catalyze a new sense of unity among humanity. In the face of a cosmos full of other life forms, our earthly differences and conflicts may seem insignificant. The discovery of life on K2-18b also raises practical questions about our responsibilities toward extraterrestrial life. If we ever gain the ability to travel to this planet, how should we interact with its biosphere? Do we have the right to interfere, study, and possibly alter this life? The history of human interactions with Earth's ecosystems does not inspire optimism. We have caused mass extinctions, destroyed habitats, and driven countless species to extinction. Should we apply the same destructive practices to extraterrestrial biospheres? Or will the discovery of life beyond Earth compel us to develop a more responsible approach to interacting with nature? There is a concept of planetary protection, a set of international guidelines aimed at preventing the contamination of other worlds with Earth microorganisms and protecting Earth from potential contamination by extraterrestrial organisms. If we send a mission to K2-18b, even a robotic one, we will have to take extreme precautions to avoid introducing Earth microbes that could disrupt or even destroy the local ecosystem. Sterilizing spacecraft is a complex and expensive process, but the price of failure could be catastrophic. We risk destroying the only known extraterrestrial biosphere because of our negligence. This is an ethical responsibility of enormous magnitude. Returning to the current situation with K2-18b, it is important to realize that we are at a very early stage of research. Even if dimethyl sulfide is confirmed, even if the biological hypothesis becomes the consensus, we will only know a small part of the full picture. We will know that there are probably organisms there that produce certain gases, but we will not know what these organisms look like, how they function, what their ecology is, how they evolved. Every answer raises dozens of new questions, and that's fine. That's what drives science forward, a constant quest for deeper understanding, never satisfied with superficial answers. Think about how long it took humanity to understand life on its own planet. Microorganisms were only discovered in the 17th century with the invention of the microscope. Before that, we didn't even know about the existence of the microbial world. The role of microorganisms in disease, nutrient cycling, and ecosystem functioning was understood even later. Molecular biology, the understanding of DNA and the genetic code, only came in the 20th century. And even now, in the 21st century, we continue to discover new aspects of Earth's biology. Deep-sea hydrothermal ecosystems were only discovered in 1977. The vast diversity of microbial life in the oceans and soils is still being cataloged. If understanding life on our own planet has taken centuries and is still ongoing, how long will it take to understand life on a planet hundreds of trillions of kilometers away? But this is no reason for despair. On the contrary, it is a reason for excitement. Each new generation of scientists will contribute to the expansion of our knowledge. Students studying astrobiology today may be the ones who develop methods for detailed study of extraterrestrial biospheres. Children born today may grow up in a world where the existence of extraterrestrial life is an established fact rather than a speculative idea. They will mature with the understanding that the universe is full of life, that humanity is part of a larger cosmic history of biology. This will change their worldview, their values, their ambitions. Perhaps this will inspire more young people to choose careers in science, seeking to contribute to humanity's greatest adventure, the exploration of space and the search for life beyond Earth. Technological advances also open up new possibilities. Artificial intelligence and machine learning are already being used to analyze astronomical data, helping to detect exoplanets, classify galaxies, and identify anomalies in spectra. As these technologies improve, they will become even more powerful tools for the search for biosignatures. AI can analyze vast amounts of data from telescopes, identifying subtle patterns that the human eye might miss. It can simulate complex atmospheric processes, predicting the spectral characteristics of different scenarios. It can even propose new hypotheses and avenues of research that human researchers have not considered. Quantum computing, while still in its early stages, promises to revolutionize our ability to model complex systems. The atmospheric chemistry of exoplanets involves millions of simultaneous chemical reactions interacting with each other in non-linear ways. Classical computers struggle to cope with such complexity. Quantum computers, using the principles of quantum mechanics, could model these systems with unprecedented accuracy, giving us a much deeper understanding of what is happening in the atmospheres of distant planets. Nanotechnology could enable the creation of miniature probes and instruments capable of performing complex scientific research with minimal mass. This is critically important for interstellar missions, where every gram of mass matters. A probe the size of a smartphone chip, equipped with tiny spectrometers, cameras, and communication equipment, could be accelerated to high speeds using a laser sail and sent to distant star systems. Hundreds or thousands of such probes could be launched, increasing the chances that at least some would reach their destination and transmit data back to Earth. biotechnology also plays a role. Synthetic biology allows us to create organisms with specific properties, adapted to specific conditions. If we ever want to colonize other worlds or establish research bases there, we could use genetically modified microorganisms for terraforming, producing oxygen, food, and fuel from local resources. Understanding the extraterrestrial biochemistry on K2-18b could inspire new approaches in synthetic biology by showing what alternative biochemical pathways are possible. As for the silence of NASA and the scientific community over the past 3 months, it is important to understand the context of the pressure researchers are under. On the one hand, there is enormous public and media pressure. Journalists demand news, enthusiasts crave confirmation, and skeptics are ready to criticize any inaccuracy. On the other hand, there is pressure from the scientific community. Colleagues demand rigor, reviewers carefully check every statement, and researchers' reputations depend on the accuracy of their work. Balancing these pressures is incredibly difficult. Researchers want to share exciting discoveries, but they cannot risk their careers and the credibility of science for the sake of premature announcements. Add to this the political dimension. Space science is funded by taxpayers through government agencies. Announcing the discovery of life on another planet has enormous political and social implications. Governments may want to control how and when such information is presented to the public. There may be concerns about panic, religious reactions, and geopolitical consequences. Although science should be free from political interference, in reality it exists in a political context, especially when it comes to funding and large projects. This adds another layer of complexity to the process of announcing revolutionary discoveries. There is also the issue of international coordination. James Webb is a joint project between NASA, the European Space Agency, and the Canadian Space Agency. The data is available to researchers around the world. Any major announcement must be agreed upon between these organizations. It takes time to consult and reach consensus on what to say and how to phrase it. In an ideal world, science would be free from such bureaucratic processes. But in reality, large international projects require coordination at many levels. It is interesting to note that the history of astronomy is full of examples of discoveries that were met with skepticism and took time to be accepted. When Galileo Galilei first observed Jupiter's moons in 1610, many scientists of the time refused to look through his telescope, and some of those who did claimed to see optical illusions. The idea that not everything revolves around the Earth was too radical to be accepted immediately. When absorption lines were discovered in the solar spectrum in the 19th century, it took decades to interpret them correctly and understand what they revealed about the chemical composition of the Sun. When Wegener proposed the theory of continental drift in the early 20th century, most geologists dismissed it as absurd. It took half a century and the accumulation of new data before the theory of plate tectonics was accepted. The moral of these stories is that radical ideas take time to be accepted. The scientific community is conservative for good reasons. It protects against mistakes and against getting carried away by fashionable but incorrect theories. But it also means that even when the evidence is compelling, the process of acceptance can be slow. In the case of K2-18b, we are watching this process unfold in real time. The data is there. The interpretation is being debated. Consensus is gradually forming. And when it is reached, when the scientific community is ready to make an official announcement, it will be a moment that goes down in history. While we wait, it is worth considering the bigger picture. K2-18b is just one planet among thousands of known exoplanets. And those thousands are only a tiny fraction of the total number of planets in the galaxy. It is estimated that there are hundreds of billions of planets in the Milky Way alone. Many of them are in the habitable zones of their stars. Many have conditions that are potentially suitable for life. If K2-18b is habitable, how many other habitable worlds are there? If life arose independently twice, on Earth and on K2-18b, how widespread is it in space? Statistics suggest that we may be on the verge of realizing that the universe is teeming with life. But not all life is the same. Even if microbes are common, complex multicellular life may be rare. And intelligent life capable of creating technology and civilizations may be even rarer. The Fermi paradox, a famous question posed by physicist Enrico Fermi. If extraterrestrial civilizations exist, where are they? why don't we see signs of their presence? Suggests that either intelligent life is extremely rare, or civilizations for some reason do not reach the level where they become visible at interstellar distances. Perhaps technological civilizations are short-lived, destroying themselves through wars, environmental disasters, or uncontrolled artificial intelligence. Perhaps interstellar travel is so difficult that even advanced civilizations do not attempt to colonize the galaxy. Or perhaps we are simply the first. The universe is 13.8 billion years old, but complex life takes time to evolve. Perhaps humanity is one of the first technological civilizations to emerge in space. The discovery of microbial life on K2-18b will not answer these questions directly, but it will give us important information. If life arises easily, but we do not see intelligent civilizations, it suggests that the transition from microbes to intelligence is extremely difficult, or that civilizations are short-lived. This would be disturbing news for humanity. It would suggest that our future may be short, that we will encounter some insurmountable filter that destroys civilizations before they reach the space stage. But if life is rare, and we have nevertheless discovered it on K2-18b, this suggests that we are incredibly lucky, or that our region of the galaxy is particularly rich in life. In any case, each new discovery helps us understand our place in cosmic history. Imagine the future, 100 years from now. Next-generation telescopes have conducted detailed studies of hundreds of exoplanets. We know which ones are habitable, which ones have biospheres, and which ones show signs of complex life. We have compiled a catalog of living worlds. Perhaps we will even have discovered signs of technological civilizations, atmospheric pollution from industrial chemicals, megastructures altering planetary orbits, radio signals of artificial origin. People of that time will look back on our era as an age of great discoveries, when humanity first learned that it was not alone. K2-18b will go down in history textbooks as the first exoplanet where convincing biosignatures were discovered. The names of the researchers who made this discovery will become familiar to every schoolchild, like the names of Copernicus, Galileo, and Darwin. But even 100 years from now, many questions will remain unanswered. We will not be able to physically visit K2-18b. We will not be able to take samples of its life for laboratory analysis. Our understanding will be limited to what we can observe from afar through telescopes, and this makes our search particularly acute. We are like children looking at a distant island through binoculars, seeing the greenery of vegetation and the movement of animals, but unable to touch, feel, or fully experience it. We know there is something there, but we cannot fully understand it. This inaccessibility, this fundamental boundary between us and extraterrestrial life, which we can detect but cannot study directly, creates a unique form of scientific and existential tension. Perhaps in the distant future, centuries or millennia from now, if humanity survives and continues to evolve, we will acquire the technology for interstellar travel. Generation ships carrying humans on centuries-long journeys to distant stars. Or cryonic ships, where crews sleep in suspended animation while automated systems guide the vessel through the void. Or perhaps something we cannot even imagine now, the use of quantum entanglement for instant communication, the manipulation of space-time to create warp drives or wormholes, the uploading of human consciousness into digital form for transmission at the speed of light. Science fiction often anticipates scientific facts. Ideas that seem impossible today may become reality tomorrow. And when humanity finally reaches K2-18b, if it ever does, what picture will we find? Will the ocean truly be teeming with life, ecosystems of microbes and perhaps more complex organisms adapted to extreme conditions? Or will we find that life there exists only in narrow niches, isolated pockets, barely clinging to existence in an environment on the edge of habitability? Will we encounter life forms so alien that we struggle to recognize them as living? Organisms with biochemistry so different from Earth's that our biologists will spend years studying them before understanding how they function? Humanity's first encounter with extraterrestrial life, even microbial, will be a moment of profound significance. Planetary protection protocols will require that we not contaminate the environment. Initial investigations will be cautious and remote. Probes descending into the ocean, collecting water samples for analysis on board, searching for cells, organic molecules, signs of metabolism. when the first sample of an alien organism is placed under a microscope, when scientists see for the first time the structure of a cell that developed in a completely different world, it will be a moment comparable to man's first step on the moon. But instead of a physical achievement, it will be an intellectual achievement, confirmation that life is a universal phenomenon, that the universe is full of biology. Let's return to the present moment. Right now, as you listen to this video, somewhere researchers are poring over computer screens, analyzing the latest data from James Webb. Statistical models are working, calculating the probabilities of various interpretations. Discussions are raging in email correspondence and video conferences between scientists from different countries. Some are writing articles, carefully wording each statement, anticipating reviewers' objections. Others are planning the next observations, choosing the optimal parameters to confirm or refute hypotheses. All of this is happening now, in real time, and the outcome of these efforts will determine how humanity will view space in the coming decades. NASA's silence over the past 3 months is not a sign that nothing is happening. On the contrary, it is a sign that a lot is happening. Behind the scenes, the drama of the scientific process is unfolding in all its rigor and caution. And when the announcement is finally made, whatever form it takes, whether it confirms the biosignature or acknowledges uncertainty, it will be the result of months of painstaking work by hundreds of people who have dedicated their lives to seeking the truth about space. It is also important to recognize the contribution of the engineers and technicians who made these observations possible. James Webb is an engineering marvel, the result of decades of development and billions of dollars of investment. Its mirrors are precise to the nanometer. Its instruments can distinguish spectral lines with incredible detail. Its solar shield protects sensitive sensors from the heat of the sun. Its orbit at Lagrange point L2, 1.5 million kilometers from Earth, provides a stable platform for observations. Every aspect of this telescope has been carefully designed to achieve one goal: to unlock the secrets of the cosmos. And now, as it observes K2-18b, it is doing just that. Without the technological advances of recent decades, we could not even dream of such observations. A generation ago, the idea of studying the atmospheric composition of a planet around another star seemed like science fiction. Now it is a reality. And in another generation, who knows what will be possible? Perhaps we will learn not only to detect biomarkers, but also to distinguish between different types of life based on their spectral signatures. Perhaps we will develop telescopes capable of obtaining images of exoplanet surfaces with sufficient resolution to see continents, oceans, clouds, and possibly even large structures, if they exist. Each technological advance opens up new possibilities for discovery. As we conclude this exploration of the mystery of K2-18b, let's return to the main question we started with. What did James Webb see on this distant planet that caused the scientific community to hold its breath? We know the answer: dimethyl sulfide, a molecule that is a biomarker on Earth. We know the interpretation. It is possible, even probable, that life exists on K2-18b. But we also know the uncertainty. Science does not provide definitive answers instantly. It requires time, verification, and confirmation. And so we wait. We wait for the next observations, the next articles, the next announcements. But even while we wait, we can feel the significance of the moment. We live in an era when, for the first time in human history, we have the tools to search for life on other planets. We live in an era when the question, "Are we alone in the universe?" is moving from the realm of philosophy to the realm of empirical science. We live in an era when the answer to this ancient question can be obtained not through faith or speculation, but through observation and data. This is a privilege, this is a blessing, and this is a responsibility. The responsibility to search for the truth thoroughly, to report findings honestly, to interpret results responsibly. K2-18b, an ocean planet under a hydrogen sky, orbiting a red dwarf 124 light-years away, may turn out to be the first confirmed habitable world beyond Earth, or it may remain a mystery, a world with intriguing chemical features, but no definitive evidence of life. Time will tell. But regardless of the outcome, the journey itself, the process of discovery, debate, and gradual approach to the truth, is what makes science humanity's greatest adventure. We look up at the sky and ask, what is out there? And slowly, patiently, methodically, we find the answers. Thank you for staying with us until the end of this exploration of one of the most exciting mysteries of our time. As the story of K2-18b unfolds, stay tuned for news from the world of astronomy. Each new observation brings us closer to the answer. And when that answer finally comes, remember, you were here at the moment when humanity stood on the threshold of the greatest discovery in its history. We don't know if we are alone. But soon, perhaps very soon, we will find out. And the world will never be the same again.